Welcome back to the Explainer. Today, we're going on a bit of a trip. Think of it as following a mathematical yellow brick road through this magical wonderland of connections, routes, and networks. We are diving into the absolutely fascinating world of graph theory. I literally love this topic because it takes all this abstract math and turns it into something you can visually map out and really explore. We're going to take our time, enjoy the scenery, and learn exactly how to navigate this incredible mathematical landscape.
So, picture this. How do you navigate a wonderland without crossing your own path? Or, how do you make sure you visit every single interesting town without ever retracing your steps? Sounds kind of like a riddle, right? Well, before we can just go running through this wonderland, solving these grand puzzles, we first need to learn how to read its map. We have to learn the language.
Section 1. Reading the graph map.
Before we jump in and try to solve anything, we gotta go slow. We need to be patient and build our vocabulary. We are really focusing on our mathematical literacy right here. So, first up, we have a vertex. Think of a vertex simply as a point in a graph. On our mathematical journey, a vertex represents our stopping points. Our cities are our towns. In other contexts, it could be a person in a social network or a computer on the internet. But for our travel purposes today, just picture it as a specific destination point.
Next, we have an edge. If the vertices are our towns, then the edges are the roads connecting them. An edge is simply a connection between two vertices. It's the literal path we walk on to get from point A to point B.
And finally, we have the degree. Now, this one is absolutely crucial. The degree is just the number of edges touching a single vertex. In our wonderland, it's really just a matter of standing right in the center of a town and counting how many different roads lead into or out of it. So, if a town has 3 roads connected to it, it has a degree of 3. Simple as that.
Let's actually put this to the test and see how it builds together on a map. I want you to pause for a sec and just read this graph with me before we even try to do anything complicated. How many vertices, or towns, do we have? 4, right? A, B, C, and D. Now let's look at their degrees. Check out vertex A on the left. If you carefully count the lines touching it, you'll see one going up to B, one going across to C, and one going down to D. That's 3 edges, so the degree of A is 3. Now absorb vertex B up at the top. It only connects to A and C, so its degree is 2. C has 3 edges touching it, so its degree is 3. And D at the bottom has 2 edges, so its degree is 2. See, you're reading the map.
Okay, there is one last vocabulary word we need before we meet the 2 famous mathematical rule sets of our journey. That word is circuit. A circuit is simply a route that starts and ends at the exact same vertex. In travel terms, it just means you can leave your house, go out on a journey, and return right back to your very own front door. And by the way, because you're returning right back to where you started, basically going in a big loop, a circuit is also called a cycle.
Section 2, Euler paths and circuits.
Now that we can read the map, let's meet the first of our 2 famous mathematical rule sets. Here is the absolute most crucial thing to remember. Euler cares about edges. If you're taking an Euler journey, your one and only goal is to walk every single road, every single edge, exactly once. You do not want to leave any road unwalked, and you absolutely cannot walk the same road twice. Now, you can pass through the same town, the same vertex, as many times as you want. Euler doesn't care about the towns. Euler only cares about inspecting every single road.
But, wait, how do we know if a map will actually let us walk every road exactly once without getting stuck? Do we just have to guess and draw lines until we're totally frustrated? Not at all. We've got a secret key. To find out if an Euler journey is even possible, we just ask, how many vertices have an odd degree? We literally just count the odd connections.
And that brings us to the brilliantly simple Euler degree rule. Remember how we counted those degrees a minute ago? Well, here is the golden rule. If all vertices are even, meaning all even, the graph has an Euler circuit. You can start, walk every road once, and end up exactly where you started. Now, if there are exactly 2 odd vertices, the graph has an Euler path but not an Euler circuit. You can walk every road once, sure, but you're going to start in one town and finish in a completely different one. And if there are more than 2 odd vertices, the graph has no Euler path whatsoever. It's mathematically impossible. And why does this make sense? Think about it. When you pass through a town, you need one road to enter and a totally different road to leave. That uses edges in pairs. So an odd degree ruins that perfect pairing, unless it happens to be the specific town where you start or end your entire trip.
This beautifully illustrates the rule. Check out this figure 8 trail. Let's read the degrees. B, C, D, and E on the outside? They all have 2 edges touching them. They're even. What about that central vertex, A? It has 4 edges touching it, also even. Because all vertices have an even degree, we know for an absolute fact we can complete an Euler circuit here. We could go A to B, down to C, back to A, up to D, down to E, and return right back to A. Every edge walked exactly once. I mean, it's just incredibly satisfying.
Section 3, Hamilton paths and circuits.
But what if we completely change the rules of our journey? Let's leave Euler behind for a second and enter the territory of Hamilton. If Euler was obsessed with the roads, Hamilton is obsessed with the destinations. Hamilton cares about vertices. A Hamilton journey asks, can we visit every vertex, every town, exactly once? Hamilton completely ignores the extra roads. You don't need to walk every edge at all. You just need to pop your head into every single town one time without ever repeating a town.
Now, what's really wild is how easily a Hamilton circuit can be ruined by a map's layout. Take this dead-end gallery. We want to visit every vertex and return home, right? But notice vertex D on the far right. It only has 1 edge connecting to it. Its degree is 1. If you enter town D, you literally have to turn around and use the exact same road to leave, which means you'd be passing through town C a second time. You just can't have a Hamilton circuit if there's a dead-end town. You have to have a way to enter and a way to leave.
Section 4, Comparing the 2 journeys.
Let's put these 2 journeys side by side, because this is where our math literacy really gets put to the test. On side 1, we have Euler. Imagine you're a bridge inspector. Your job is to inspect every road and cross every single bridge exactly once. Your focus is strictly on the edges. Then on side 2, we have Hamilton. Imagine you're a tourist on a really tight schedule. Your job is to visit every city and stop at every station exactly once. Your focus is strictly on the vertices.
This is such a fascinating contrast. On the left, we have our figure 8 graph. Now, we already proved it has an Euler circuit because all the degrees are even. But does it have a Hamilton circuit? No way. Because to visit the towns on the left and the towns on the right, you'd be forced to pass through that center vertex A twice. So having an Euler circuit absolutely does not guarantee a Hamilton circuit. Now check out the square with the center vertex E on the right. Can we do an Euler journey here? Well, let's count the odds. Vertices A, B, C, and D all have 3 edges connecting to them. That's 4 vertices with an odd degree. And remember the Euler degree rule. More than 2 odd means no Euler path. Period. But does it have a Hamilton circuit? Yes. Just walk the outside border. A to B, to C, to D, then jump into the center E and go right back to A. Boom! You visited every town exactly once.
The really big takeaway here is that meaning comes from context and definitions, not just the names. Graph theory is a language. Euler and Hamilton problems are both just asking us about moving through a map, but they measure success completely differently. A map tells us a very different story depending on what kind of rules we decide to apply to it, and that is exactly why we take our time to truly understand the definitions.
Section 5, Real-World Graph Applications.
Now you might be wondering, is this all just a fun brain teaser, or does this wonderland actually connect to our real world? Oh, it absolutely does. We use these rules every single day. Take a mail carrier. A mail carrier's entire job is to deliver mail to the houses on the streets. They need to walk every street segment exactly once to be perfectly efficient. That is a real-world Euler problem. Now think about a school field trip to a massive museum. The teacher definitely doesn't want to walk every single hallway in the building. That would take all day. They just want to visit 5 specific museum exhibits exactly once and then hustle everyone back to the bus. That is a real-world Hamilton problem.
So, as we wrap up our journey through this mathematical map today, I want to leave you with this question to ponder. Next time you walk a path, will you count the roads you take or the stops you make? Will you be taking an Euler journey or a Hamilton journey? The world is really just one giant graph waiting to be explored. Thank you so much for joining me on this explainer. Keep asking those great questions, and I'll catch you next time.